Right, as promised, let's talk about isotopes now. So, isotopes. As you can see, my pen's decided it's going to start mistriggering, so that's excellent, and are going to help my task a great deal. The easiest way of working out what isotopes are is probably to start where we left off last time. So let's do carbon 12-6. But of course there are other types of carbon. So we've got carbon 11-6, carbon 13, and the one that most people are aware of, carbon 14. Notice they're all 6 because they're all carbon. It's the proton number that dictates which element it is. The nucleon number at the top is what we're going to be talking about for this session. Now, if you ask people which of those are isotopes, in my experience, most people will go isotope, 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 not an isotope. And I think that the reasons that they give often, well, this is normal carbon. You know, this is the kind of bring it home to meet your mum carbon. These are the isotopes. They're often unstable, a little bit nutty, a bit mentalist. Don't want them anywhere near your family. So they kind of identify this as being what we call carbon, and the other ones as being something a bit different, and therefore they identify the word isotope as being something, you know, a bit different. In fact, if you know your stuff, they're all isotopes. Every single atom in the universe is an isotope. Isotope is a way of differentiating. I don't mean that in a calculus manner, of telling the difference between different atoms of the same element. So every atom of carbon is an isotope of carbon. Which rather begs the question, why do we have this idea then? And I think it goes back to the way we actually teach elements and stuff full stop. So let's have a look at that. So let's have a look at why people will think, yes, isotope, 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 no. I think it's the way we teach this lower down when people are first learning. Because we want them to focus on the science, not the maths, we don't tend to use atoms and elements and stuff with large numbers. So, you know, use helium. Now helium's only 4 too. How very weeny. Let's look at carbon. Yep, 12-6. How about some nitrogen? 7-14. Now in the words of our Lord Rolf, can you see what it is yet? Okay, let's bung neon on the end just to continue a fairly obvious run. Oh look, I take it you've got it by now. If you take the proton number away from the nucleon number in each of these cases, you are going to get that the number of protons is equal to the number of neutrons. 7, 7, 8, 8, 10, 10, etc. Were we to write it generically, so what I'm going to do is come over here. I didn't do this in the last video because I thought, you know, there's enough going on in that. If we wrote X as meaning standing for any element, so generically for any element, the number up the top, the nucleon number, we give the symbol A, and the proton number, you can see why A for atomic number, can't you? Sorry, atomic mass. If you come down here, Z, why? I presume the king of chemistry got drunk on some ethanol and decided to call it Z. I don't know, and the emperor of physics didn't intervene in time, who knows. But they call it Z, maybe alpha and omega, I don't know, maybe there's a religious motif. But anyway, nucleon number, proton number. If you look at all of these, it's fairly obvious, you should find that the nucleon number is equal to 2 times the proton number, and right there's why I cross my Z's so you don't get confused. And because we do small atoms where this relationship dominates, I think that's why people tend to think, well, proper atoms, normal atoms, have this relationship. And as soon as we move away from this relationship, it's not a proper atom, it's a weird atom. And so they appropriate the word isotope to mean weird atoms that aren't used to the ones I'm looking at, and specifically this. Of course, that is rubbish, as we'll now have a look. It's not even English. Anyway, let's look at a few atoms that go beyond neon. Let's look at sodium. Sodium does have 11, it just continues the proton number on, but, goodness gracious me, it isn't 22, it's 23. Let's look at iron, which obviously has the symbol Fe. Oh, God bless Latin. 26, but not 52. 56. Lead. I do apologise on behalf of the periodic table for lead being PB. 82 and 207. What a whopper. And let's go to uranium. Everyone does uranium at some point. So let's have a look at this. 92. And if we look up the top, it's 238. That is one fat atom. Now, it's fairly obvious, I think. If we subtract that from there, what we discover is that obviously what we've got here is 12 neutrons. And so that's one more than the number of protons. If we do this here, we get 30 neutrons, which of course is 4 more neutrons than protons. If we do this, we get 125. That's quite a lot, which is 43 more neutrons than protons. And if we keep going up, we get 146 neutrons, which is an additional 54 neutrons over and above the number of protons. Now, first of all, we can see that this completely blows apart the idea that you've got to have the same number of neutrons and protons and all that stuff we've talked about before. These are the abundant forms of these elements. They're not the weird ones, they're the normal ones, and that's broken down. You can also see, I hope, that as the atoms get larger and larger in terms of their mass, this difference increases also, and there is a reason for that. And that reason I will reveal, like some sort of mental Wizard of Oz, when we do bosons and the strong nuclear force and stuff like that. But for the moment, all you need to realise is that there is this relationship. It gives what we're talking about before a massive kicking, and therefore the isotopes, well, everything's an isotope. You don't have to have some sort of weird mental tick about comparing things and working it out from there. So how are we going to define isotopes? Well, if you look on the sevens, I've defined isotopes as saying atoms with the same number of protons but differing numbers of neutrons. And there is a reason for that. A lot of textbooks say atoms with the same number of protons but different number of neutrons. Well, I think that's plugging back into what we looked at here, that the number of protons and neutrons are different in an isotope. So I just prefer differing because it's slightly more elegant linguistically, and it doesn't reinforce this kind of old rubbish here. Just a couple of more things to say before we wrap this one up. Obviously, what we're finding out as we go further and further along here is that the A number is no longer equal to 2 times the Z number. In fact, it's getting significantly greater than 2 times the Z number. That's the first thing we need to say. Also, I know this might sound strange, but here's ion, here's isotope, which I'm really emphasising how I say it. I know they've both got an I, and O's in it, but they're really not the same thing. I know you've met 2 new words that have an I at the front and O's in them. Isotopes and ions, not the same thing. I think we'll leave it there because there's some other stuff that I can talk about in the next tutorial. Hopefully this has made sense. Just to wrap it up, everything's an isotope. Every element in the universe is an isotope, and they're just atoms with the same number of protons but differing number of neutrons. If we go all the way back up to the top and have a quick look at how that pans out, let's go up here. Oh look, these are atoms with the same number of protons, which means they're all of the same element, but they have differing numbers of neutrons, 5, 6, 7, and 8. And as I said, you'll tend to find the ones that are non-abundant. In other words, they're not the main one, the common one. Doesn't necessarily have to have this relationship, as you can see, looking down here. These tend to be unstable, and we'll discuss that a bit later when we do strong nuclear force.